In this lecture, we are looking at the application of the root locus in the design of discrete control systems. As a review, a root locus is the trajectory of closed-loop poles when some parameter varies. It is used for stability investigations and locating dominant poles at specific positions in the z-plane in order to meet a performance requirement. In the z-plane, the stability boundary is the unit circle. To obtain the root locus problem, the closed-loop characteristic equation is expressed in the form 1 plus alpha fz equals 0. Alternatively, it can be expressed as fz equals minus 1 over alpha. Alpha is some variable system parameter such as gain. Fz is known as the open loop TF of the root locus problem. It is the part of the closed loop characteristic equation that does not depend on the variable system parameter. A point will lie on the root locus if it satisfies two conditions. One, the phase condition. The phase of Fz at the point must be an odd multiple of 180 degrees. Two, the magnitude condition. The magnitude of Fz at the point must be equal to 1 over alpha if we take alpha as being more than 0. As a review, the general features of the root locus are 1. It is symmetrical about the real axis. 2. It is made up of a number of branches. The number of branches is equal to the order of the system. As an example, the root locus for a third-order system has 3 branches. 3. Each branch starts on an open loop pole and finishes on an open loop 0. The open loop poles and open loop zeros are the poles and zeros of the open loop TF of the root locus problem. If the number of open loop zeros is less than the number of open loop poles, then some of the branches will finish at infinity along an asymptote. Therefore, the number of asymptotes is equal to n minus m, where n is the number of open loop poles and m is the number of open loop zeros. Let's go through the steps that are followed when constructing the root locus. The first step is to plot the open loop pole zero map. Obtain the open loop zeros and the open loop poles from the open loop TF of the root locus problem and place them on the z-plane. The second step is to obtain the portions of the root locus that lie on the real axis. The rule is, look at the open loop poles and open loop zeros that lie on the real axis. Portions that lie to the left of an odd total number of poles and zeros lie on the root locus. Draw line segments to indicate these portions. If there are asymptotes in the root locus, the next step is to obtain the asymptotes. The asymptotes intersect at the point sigma on the real axis. The value sigma is equal to sum of open loop poles minus sum of open loop zeros divided by number of open loop poles minus number of open loop zeros. The angles that the asymptotes make with the real axis are given by theta equals 2q plus 1 in brackets by pi divided by n minus m. N is the number of open loop poles, m is the number of open loop zeros, and q is an integer that ranges from 0 up to n minus m minus 1. The next step is to obtain the breakaway and the break-in points. Express the root locus problem in the form alpha equals minus 1 over fz. The breakaway and break-in points are the turning points of alpha. Obtain these points by setting d alpha dz equals to 0. To determine if a point is a break-in or a breakaway point, obtain the second derivative of alpha with respect to z. If the second derivative at the point is less than 0, the point is a breakaway. If the second derivative is more than 0, then the point is a break-in. Alternatively, if the point is between poles, it is a breakaway point. If the point is between zeros, it is a break-in point. If there are complex open loop poles and open loop zeros, there is need to determine departure and arrival angles. The angle of departure from a complex open loop pole is equal to 180 degrees minus sum of angles from other open loop poles plus sum of angles from open loop zeros. The angle of arrival at a complex open loop zero is equal to 180 degrees minus sum of angles from other open loop zeros plus sum of angles from open loop poles. To obtain the point at which the root locus crosses the imaginary axis, put jy in place of z in the characteristic equation. Equate the real and imaginary parts to 0 to solve for y and alpha. Y is the point on the imaginary axis at which the root locus crosses the imaginary axis. Alpha is the value of the system variable parameter at the point when the root locus crosses the imaginary axis. To obtain the point at which the root locus crosses the unit circle, use the Jury's stability criterion. Using this criterion, find the values of z and alpha for which the system becomes just unstable. Z is the point in the z-plane at which the root locus crosses the unit circle. Alpha is the value of the system variable parameter when the root locus crosses the unit circle. Let's illustrate the construction of a root locus using an example. We wish to implement a controller of the form kz over z minus 1 in the system shown. K is a variable parameter in the controller. As a design aid, we want to investigate the trajectory followed by poles when K is varied. First, we obtain Gz, the TF of the process, preceded by a zero-order hold DAC. It works out as 0.39 over z minus 0.61. The closed loop characteristic equation can be worked out from 1 plus dz gz equals 0. Hence, we obtain it as 1 plus k by 0.39z over z minus 1 in brackets by z minus 0.61 in brackets equals 0. For the root locus problem, the system variable parameter is k and the open loop TF is 0.39z over z minus 1 in brackets by z minus 0.61 in brackets. Therefore, the open loop 0 is 0 and the open loop poles are 0.61 and 1. Since the system is of second order, it means that the root locus has 2 branches. Thus, the pole 0 map for the open loop poles. And these are the segments of the root locus that lie on the real axis. The segments are the portion from 0.61 to 1 and the portion from 0 to minus infinity. There is only one asymptote because the difference between the number of poles and zeros is 1. That asymptote is the negative real axis. To get the breakaway and break-in points, we make K the subject of formula in the root locus problem and determine the turning points of K. We get the breakaway and break-in points as 0.78 and minus 0.78. 0.78 is between poles, therefore it is a breakaway point. Minus 0.78 is between zeros, therefore it is a break-in point. This is what happens. The two branches of the root locus start from the respective open loop poles 0.61 and 1.0. They move towards each other until they break away at the point 0.78. After breaking away, they move into the complex plane and then break in at the point minus 0.78. After breaking in, one of the branches moves from minus 0.78 to 0, and the other branch moves from minus 0.78 towards infinity along the negative real axis. The critical value of K is equal to the magnitude of the open loop TF when Z equals minus 1. In other words, it is the magnitude of the open loop TF when the root locus crosses the unit circle. Therefore, the range of K for stability is from 0 to 8.26. We have already mentioned that the root locus is applied in the design of controllers. The steps that may be followed when using the root locus to design a controller are: 1. Determine the position of the dominant closed loop poles from the performance specification requirements for the system. 2. Draw the open loop pole zero map and calculate the root locus angle at the dominant pole position. This angle is determined from the relationship between the root locus angle at a given point and the angles that vectors from that point to other open loop poles and open loop zeros make with the horizontal axis. Geometry may be used to calculate the angle. 3. Calculate the extra phase angle needed to make the dominant pole to be on the root locus. In other words, calculate the extra phase angle to make the root locus angle to be minus 180 degrees. 4. Decide on a suitable form of the controller and calculate the controller poles and zeros required to meet the phase condition. The controller is responsible for the extra phase angle. Therefore, the phase angle is a function of the positions of the poles and zeros of the controller. To obtain the poles and zeros, we put them as unknowns when calculating the phase angle and solve the equation with the condition that the phase angle must be equal to minus 180 degrees. 5. Calculate the gain of the controller. The gain of the controller is determined from the root locus magnitude condition. Here is an illustration. P is the position of the dominant closed loop pole in order for the system to meet the given performance requirement. P1 and P2 are positions of the open loop poles of the system. Z1 is the position of the open loop zero for the system. Theta 1, theta 2, and phi are angles that vectors from P to the respective poles and zeros make with the real axis. The root locus angle at point P is given by sum of angles from zeros minus sum of angles from poles. In this case, the angle is equal to phi minus theta 1 plus theta 2 in brackets. In order for the system to meet the given performance requirement, the the point P must lie on the root locus. In other words, the root locus angle must be equal to minus 180 degrees. To make this angle to be minus 180 degrees, we can add poles and zeros to the system. These poles and zeros are introduced by a controller. The poles and zeros will introduce new angles in the calculation of the root locus angle for the point P. Therefore, we can carefully select these angles and therefore the positions of the poles and zeros to make the point P to be the root locus. In the S-plane, the dominant poles are located at the points given by minus zeta omega n plus or minus j omega n by square root of 1 minus zeta squared. When mapped into the Z-plane, the dominant poles are going to be located at the points given by z equals e to the minus t zeta omega n times e to the plus or minus jt omega d. If we substitute for t using t equals 2 pi over omega s and for omega n using omega n equals omega d over square root of 1 minus zeta squared, we obtain the magnitudes of the dominant poles as e to the minus 2 pi zeta over square root of 1 minus zeta squared times omega d over omega s. The arguments of the dominant poles are obtained as plus or minus 2 pi omega d over omega s. The standard controller forms are: for proportional controller, dz equals kp. Therefore, it does not introduce any pole or any zero. Integral controller, dz equals kiz over z minus 1. Therefore, it introduces a pole at 1 and a 0 at 0. PI controller, dz equals k z minus a over z minus 1. Therefore, the controller introduces a pole at 1 and a 0 at the point A. We can select a value for A. Therefore, we can select the position at which the 0 is going to be located. PD controller, dz equals k z minus a over z. It introduces a pole at 0 and a 0 at A. We can select the position at which the 0 is going to be introduced. For the general format of a controller, dz equals k z minus a over z minus b. In this case, the controller introduces a pole at B and a 0 at A. We can select the points at which the pole and the 0 are introduced. Let's illustrate the use of the root locus in the design of controllers using an example. For the system shown, the specifications require the damping ratio to be 0.5, the sampling time to be 0.5 seconds, and there should be 8 samples per each damped oscillation. The controller is a PI controller, that is dz equals k z minus lambda over z minus 1. We need to get a value of k and a value of lambda so that the system meets the required specifications. The first step is to obtain Gz, the TF of the process preceded by a zero order hold. It works out as 0.39 over Z by Z minus 0.61. From the closed loop characteristic equation of the system, the root locus problem for the system comes out as 1 plus K by 0.39 by Z minus lambda in brackets divided by Z minus 1 in brackets by Z minus 0.61 in brackets equals 0. The open loop 0 is at lambda. The open loop poles are at 0, 0.61, and 1. The illustration shows the open loop pole 0 map for the system. From an earlier discussion, the magnitudes and the arguments of the dominant poles are described by the expressions shown. Now, omega d over omega s equals 8 and zeta equals 0.5. If we substitute these into the expression that describe the dominant poles, we obtain the arguments of the dominant poles as plus or minus 45 degrees. The magnitude of the dominant poles is obtained as 0.635. Therefore, the dominant poles lie at the points 0.45 plus or minus J 0.45. Let's consider the dominant pole that lies in the upper half of the z-plane, that is the point 0.45 plus J 0.45. In the diagram, we represent it as P. 45 degrees, theta 1, phi, and theta 2 are the angles that the vectors erected from point P to the respective poles and zeros make with the real axis. Theta 1 and theta 2 can be obtained from the geometry of the diagram. Let's consider theta 1. The vertical distance from the point P to the horizontal axis is 0.45. The distance from the point at which a line erected from P crosses the horizontal axis to the pole at 0.61 is 0.16. Therefore, we can use trig ratios to obtain the angle theta 1. In this case, theta 1 equals 180 degrees minus the inverse tangent of 0.45 over 0.16. It works out as 109.6 degrees. We can apply a similar argument to theta 2. We obtain it as 140.7 degrees. In order for the system to meet the required specifications, the point P must lie on the root locus. Therefore, at point P, the sum of angles from zeros minus the sum of angles from poles must be an odd multiple of 180 degrees. In this case, phi minus open bracket 45 degrees plus theta 1 plus theta 2 close bracket must be equal to minus 180 degrees. If we substitute known values into the equation, we obtain phi as being equal to minus 115.3 degrees. Now we want to obtain lambda, which is the point at which the zero of the controller is located. We use the same approach as the one used to get the values for theta 1 and theta 2. However, in this case, instead of obtaining an angle, we are obtaining the value lambda. Let's apply the trig ratios to the diagram. Tan 180 degrees minus 115.3 degrees is equal to 0.45 over lambda minus 0.45. If we solve the trig equation, we obtain lambda as being equal to 0.66. From the magnitude condition, at the point 0.45 plus J 0.45, we obtain K as being equal to 1.11. Therefore, the required controller TF is dz equals 1.11 by z minus 0.66 in brackets divided by z minus 1. The corresponding algorithm is UK equals UK minus 1 plus 1.11 EK minus 0.73 EK minus 1. I recommend that you do these questions from chapter 9 tutorial questions. This is the last video in this series of lecture videos.